Good morning. Today we will continue with X-ray detectors, X-ray counters. There are many types of X-ray detectors, from photographic film to scintillation counters, gas ionization chambers, and CCD detectors, CMOS detectors. So depending on the applications, they have advantages and disadvantages. Of course, depending on the production technologies of these detectors, they have also advantages and disadvantages in terms of their price. Okay, within this lecture, of course, I will not explain all the details about X-ray detectors. I will only mention some principles of main detector types used in X-ray science and technology, also for medical applications. And after this lecture, with the knowledge you have learned here, you can easily understand other types of X-ray detectors or photodetectors. There are some useful books. The first one, Radiation Detection and Measurement, is mainly written for nuclear physics experiments, nuclear physics detectors. But since the main detector mechanisms are more or less same, this book is also very useful to understand the mechanisms of X-ray detectors. And within this book, X-ray Science and Technology, there is also a part concerning the X-ray detectors. But what I would like to tell you that the X-ray detectors are developing very fast. Every decade, new types of X-ray detectors appear for medical applications, for astronomy applications, for scientific applications, okay? Then the knowledge you get from these books cannot be enough, okay? But within the scope of this lecture, of course, you don't need to cover all the information related to the X-ray detectors, but you will have at the end the principles of X-ray detectors. So within this lecture, I will talk about photographic film, very first one in X-ray science and also for medical applications. And I will talk about gas ionization chambers, proportional counters, and Geiger counters. Actually, they have more or less the same mechanism. I will go into detail. And I will talk about scintillation counters. And we will discuss the semiconducting detectors. They are also very commonly used for scientific purposes. And we will finish with CCD detectors. They are also very common for medical applications and also for many areas. So now let me start with the photographic film. One of the first detectors used for X-rays, and in some places still used for medical imaging, okay? So what do you see here? There is a radiograph of a chest. So there are bones and soft tissues. So by using photographic film, you can get the picture of the chest. You can get the picture of other parts of the body. But this type of detectors, photographic films, have some disadvantages. So especially for scientific purposes, it is very difficult to calibrate, okay? And then, due to the production procedures of these photographic films, I mean the main material used here, they are affected by temperature and humidity, and they cannot be reused. These are the main disadvantages of these photographic films. And also, in order to store them for a long time, you have to build special conditions. Otherwise, you will lose the information on these photographic films. So it is no longer preferred as a detector in scientific studies, but for medical applications, in some hospitals, they are still used, but they are also mainly replaced by the digital detectors, which I will mention today. So what is the main working principle of these detectors? Let me draw here. Let's consider here we have an X-ray source, and here there is a patient. Then here there is a photographic film. So when you expose this person here with X-rays, the bones in the body and soft tissues will behave differently because they have different linear absorption coefficient, they have different thickness. So let me remind you here the formula: intensity is equal to initial intensity times E over minus mu T. So mu is the linear absorption coefficient of the material and T is the thickness. So within the body we have bones, right? Here, for example, we have bones. Here we have bones, and we have also soft tissues, right? For example, lungs here. So the linear absorption coefficient of the bones and soft tissues are different. In addition to that, even bones have different thicknesses within the body, right? So then X-rays are partially blocked by dense tissues such as bone and pass more easily through soft tissues. Due to this relation here I have written, areas where the X-rays strike darken when developed, causing bones to appear lighter than surrounding soft tissues. So what is the material on this photographic films? Photographic films are usually transparent film, and one side of this transparent film is coated with a gelatin emulsion which contains microscopically small crystals. These are light sensitive silver halide crystals. Okay, let's consider that here there's a person and this is the photographic film, and here on the left side you have an X-ray source. So you exposed this person with X-rays, and then some portion of the X-rays are transmitted, and then you exposed this photographic film with X-rays. Of course, depending on the soft tissues and bones, you produce different intensities on the surface of the photographic film, right? So depending on the intensity, you will have dark points and light points. So what is the meaning of dark point here? So in the dark points, when the silver halide crystals are exposed with X-rays, you produce grains, okay? And after chemical bath, you develop this silver halide grains, and then you have metallic silver here. Then on the transparent substrate of the photographic film, you have dark regions and white regions, let's say. Okay, so this is the main principle of the photographic film. Is something unclear, Nora?
No, it's clear.
Okay. So let me continue with the second one, gas ionization chamber. So here again you have an X-ray source, and this is the gas ionization chamber. Here we have an electrode, and here we have an electrode, another electrode. This is negatively charged, this is positively charged. And here we have inert gases. For example, helium, neon, argon, okay? Inert gases. Here we have a window, okay? Which is transparent for X-rays with low mu material, let's say. And then X-rays can enter into this chamber filled with inert gases, and then X-ray interact with the gas atoms within the chamber. So you have already learned the absorption mechanisms within the last lecture, right? So due to the absorption of X-rays, you produce photoelectrons, Auger electrons, or fluorescence X-rays, mainly photoelectrons. So then you ionize the atoms within this chamber, right? So then you have electrons, negatively charged electrons, and we have positively charged ions, gas atoms. So since this plate is negatively charged and this plate is positively charged, then the electron will move in this side and ions, positively charged ions, will move in opposite side. So then we will have a current. So what do you see here? We have an X-ray, and X-ray is converted to the current. Okay, so the amount of current here you measure is proportional to the incoming X-rays. So the number of the incoming X-rays. Is it clear? Any question?
No.
Let me give you some more information about this type of detectors. We generally apply 200 volt between these two plates, okay, in gas ionization chambers. And if you design this chamber carefully, I mean in terms of its dimension, and if you use proper gas atoms for certain incoming X-ray energies, then the efficiency of this type of detectors can reach up to 100%. What is the meaning of the efficiency? Let's consider that here you have an X-ray source and 10 X-rays enter into this gas ionization chamber, and then you produce 10 electron ion pairs. Then here, let's say you have a related current for this 10 X-ray. So you have counted all of them. So the efficiency of the detector is 100%. But let's consider that a worst case, 10 X-rays enter into the chamber, and then you can only count one of them, okay? Then the efficiency is 10%, okay? You can only count one of 10 photons. So energy is very important. I mean, the type of the inert gas within this chamber is very important, and it depends on the X-ray energy. Why? Because each atom has certain ionization energy, right? We have discussed binding energy of the electrons in the atoms. So in order to ionize these gas atoms, you have to use proper incoming energy to ionize these gas atoms and then produce electron ion pairs. So if you design carefully and if you choose proper gas atoms within this chamber, you can reach efficiencies up to 100%. Any question here?
Yes, teacher,
Please.
is it possible for that electrons and positive ions to recombine back together to form natural atoms, or it's not possible?
Okay, so good question. It may happen, but if you carefully design the distance of the plates, okay, I mean here there's a certain distance and you produce electric field. So in order to avoid such cases, you have to design these chambers carefully. And the applied voltage also matters in the design of this type of gas ionization chambers, and I will talk about this in the forthcoming transparencies.
Okay.
So here we have a proportional counter. The mechanism is same as gas ionization chambers. We will use again gas atoms within the chamber, okay? So now we have a cylindrical chamber and we have gas atoms. This is the inlet for the gas atoms. This is the outlet. So this is gas in, gas out. So you always use fresh gas atoms within the detector, right? Then what about the positively charged and negatively charged plates? In case of this type of cylindrical counters, here we have a positively charged rod in the center, and we have a negatively charged plate in the inner wall of the cylinder. Okay, then you have positive charge and negative charge within the detector. So here there is a window for the incoming X-rays. X-rays enter into the chamber and you have gas atoms within the chamber, and then you ionize the gas atoms and produce absorption products. photoelectrons, Auger electrons, and fluorescence X-rays. Okay, so photoelectrons and Auger electrons are accelerated under the voltage between the anode material and cathode inner wall of the cylinder. Then you produce current. Okay, so signal goes to the electronics. So what we have done here, we have converted X-rays to the current, and here we have converted X-rays again to the current, okay, by using electron-ion pairs. Any question? But
No, it's clear.
in case of proportional counters, we apply more voltages between cathode and anode here, so between positively and negatively charged plates. Here, in case of gas ionization chambers, I talk about more or less 200 volts, but in case of proportional counters, we apply 600 volts, okay? So what is the aim of this higher voltage between anode and cathode material? So remember the information from physics. Let's consider this is the positively charged, this is negatively charged, okay? You use a voltage source here, and then you have an electron here. Electron is negatively charged, and it will have certain kinetic energy from negative to positive side. So what is the source of this kinetic energy? It is due to the Lorentz force acting on the electron due to the electric field between these two plates. So what was the magnitude of electric field? It is given by voltage applied between plates over the distance between the plates, right? So if you increase the voltage, then you will increase the electrical field. If you increase the electrical field, you will increase the load acting on the electron, then you will increase the velocity of electrons. So electrons will be more energetic compared to the gas ionization chambers with the applied voltage of more or less 200 volt, okay? So in case of proportional counters, we have more energetic electrons. So what is the meaning of more energetic electrons? Let's consider that one X-ray enters into the chamber here in proportional counter, and then you produce a positively charged ion, a negatively charged electron, okay? And then this electron is accelerated from negatively charged inner plate of the cylinder to the positively charged rod in the center. You accelerate this one. Then this electron has huge kinetic energy, okay? So with its huge kinetic energy under high voltage between the plates, this electron can produce secondary ionizations, okay? So by using the energy of this electron, you can produce another electrons, another free electrons within the system. So this is called as multiple ionization, or it is also called as gas amplification, okay? So by using a single X-ray, you produce many electron-ion pairs, okay? By applying high voltage between the cathode and anode material. So the number of subsequent ionizations produced by the initial ionization is proportional to the energy of the X-rays. For this reason, we call this type of detectors are proportional counters. Do you have any questions here?
No.
So now let me finish this type of detectors with Geiger counters or Geiger-Müller counters. So the working principle is the same as proportional counters, gas ionization chambers. So the main difference is that you apply higher voltages compared to the proportional counters and gas ionization chambers. So here, gas amplification versus applied detector voltage bias curve. This is the gas amplification This is the applied detector voltage bias. So what I mean, what was the gas amplification? We are talking about multiple ionization if you apply higher voltages between anode and cathode, right? So here, this is the applied voltage. For example, in gas ionization chambers, we apply, let's say, 200 volts. And in case of proportional counters, we apply 600 volts, let's say. And in Geiger region, you apply higher voltages. So what do you see here? Here, you get ion electron pairs with this number. But here, in proportional region, you get more ion electron pairs. And in the Geiger region, you can even get more ion electron pairs. Okay, then you convert the X-rays to the current. Okay, here we have a certain range. If you further increase the applied detector voltage bias between anode and cathode material, an arc discharge will occur. So what is the meaning of arc discharge? Let me draw here negatively charged plate. Here we have positively charged plate, and then here we have a voltage source. Okay, here we have an electron, and here there are ions. So since electrons are negatively charged, they will move in this direction from negative to the positive, and ions will move in opposite direction from positive to negative, right? So if you increase the detector bias voltage here, you will produce more energetic electrons and you will produce more energetic ions. So if you further increase the voltage, what will happen? This is the negatively charged plate or cathode. This is the anode, okay? And here you collect electrons. Here you collect ions. If you increase the gas amplification too much, here you will collect many electrons. Actually, at the beginning, this plate is positively charged. I mean, it is anode material, but due to the many electrons on the surface of this anode material, you will produce a negatively charged electron cloud on the surface of the anode. Then the other electrons coming from this side to the anode will feel a repulsive force due to this negatively charged cloud here, and also same for this positively charged ions on the cathode side. So then arc discharge will occur. Okay, so then the working range of the Geiger detectors is defined by considering this effect in the detectors. Any question here?
No.
Okay, let me continue with the scintillation counters. These are also very important X-ray detectors and used in many laboratory X-ray machines. So I will talk about the working principle of this type of detectors, but let me tell you first of all that their energy resolution is 2-3 times better than proportional counters. So there is a scintillator here within the scintillation counters. What is the aim of this crystal here? There is an incident radiation, let's say hard X-ray with very high energy, okay? And with the X-ray matter interaction within this crystal, you produce light photon, okay? So you produce fluorescence X-rays. So here you have crystal, certain crystal material. I will talk about this. And then you have atoms within this crystal, and X-rays are coming with high energies. And due to the absorption mechanism, you produce a fluorescence X-ray, okay, which has lighter energy compared to the incoming X-rays. So this crystal here is called as scintillator because you send an X-ray and then this crystal produces another photon, another X-ray. For this reason, it is called as scintillator. What about the material used here as a crystal? Generally, thallium activated sodium iodide or sodium activated cesium iodide or bismuth germanate are used as crystal material here. Of course, why we are choosing different materials depending on the incoming X-ray energy. Each atom, each element has certain absorption energies, okay, certain binding energies. So depending on the incoming X-ray energy, you have to choose a proper crystal also here, as we have done in the gas ionization chambers, right? Here, depending on the incoming X-ray energy, you have to choose proper inert gas atoms. And here, in scintillation counters, you have to choose proper crystal material for incoming X-rays. So this is the scintillator part of the scintillation counters. And then we have another part, which is called as photomultiplier tube, PMT. Now I will explain the principles of this photomultiplier tube. Here we have a light photon, fluorescence X-ray, and here we have a photocathode. So what is the main aim of this photocathode? This is negatively charged, and this fluorescence X-rays, light photons, come on this photocathode material and interact with this photocathode and produce electrons. Okay, another absorption mechanism occurs here. Then you produce electrons, and these electrons are focused by using electrodes and then directed to the anode material here. This anode material is positively charged. Here we have positively charged anode material, and this photocathode is negatively charged, okay? So from photocathode to the anode material, you accelerate electrons. So what happened? Here we have very energetic X-rays. They are coming to the crystal, to the scintillator, and then you convert them to the light photon fluorescence X-rays. And here you produce electrons. You convert fluorescence X-rays to the electrons, and then you direct them to the anode material. And between photocathode and anode material here, you accelerate electrons. Since electrons are accelerated here, they are very energetic and they can produce another electrons. They can take electrons from the atoms of anode material here. So if you send one electron here, then you can have two electrons. So this is another anode material, but it is higher positive potential than this one. Then electrons, these two electrons are accelerated here, and then each of them produce another electron. Then here we have 4 electrons from this anode to another anode. Then this has higher positive potential than this one. And then they come here, they come here, they come here, they come here, they come here. So finally, they are converted to the electric signals, okay? So what we have done, we have X-ray here, and here we have converted X-rays to the current, okay? So this is the working principle of photomultiplier tube. So what you have here, you have photocathode negatively charged. Here we have anode material, another anode with higher potential, another anode material with higher potential, another anode material with higher potential. And this neighboring anode materials, this ones are called as dinode, okay? You have 2 anode material, and each of them has higher potential compared to the previous one, and then you produce an electron cascade or avalanche, okay? So then just a single X-ray is converted to many electrons here at the end. Then you have a current. So this is called as photomultiplier. Actually, you multiply, you increase the number of the electrons, okay? But since at the beginning you have photon and you convert this photon to the electron, and then you multiply this electron. The name is photomultiplier tube. Do you have any question here?
Teacher, when you said that every second ion has to be greater than the previous one, I mean, if it's the same, then this will not happen, or what could them have the same voltage?
Okay, so let's consider that this is positively charged and this is also positively charged, but the same potential, okay? So electrons are coming here, then they should have a reason to come here. So since they are happy here with this potential, they will not come here. So in order to take them from this anode material to this anode material, this one must be higher positive potential. Then we can take them to this anode material.
You mean the voltage difference for the voltage difference?
Yes, yes.
Okay, I got it, thanks.
Never mind. Okay, then let me continue with the semiconductor detectors. These are very widespread in synchrotron light sources and also for laboratory applications, and also for many applications. They are very widespread because they are very small and durable. Of course, their price depends on their design, but I can tell you that they are cheaper compared to the other complicated detectors. So you can find many different sizes and design of this type of semiconducting detectors. So they are small and durable. What I would like to tell you here that so you can use them many years, let's say, okay? So what we have within the semiconductor detectors, you can understand from the name, we use semiconducting materials. Mainly silicon is used and germanium is used. So germanium requires cooling, so silicon is widely used. In addition to these two materials, gallium arsenide, cadmium telluride, and also cadmium zinc telluride are also used depending on the applications, okay? Of course, again, depending on the application, each of them has advantages and disadvantages. And of course, production of, for example, cadmium zinc telluride or cadmium telluride or gallium arsenide require very complicated methods, okay? So depending on the material you use in the semiconductor detector, the price will change, okay? Silicon is the cheapest one, let's say, and the most common one. So many semiconductor detectors are made from silicon, let's say. So, but what is the mechanism? So what happens if X-ray enters into the active area of the semiconducting detectors? So here we have active area, here we have active area, active area. So X-ray photons are coming to the surface of this detector. So what happens? When the X-ray interacts with the photodiode, it excites an electron in the valence band to the conduction band. Then what do you have? You have electron-hole pair, like electron-ion pairs in gas ionization chambers. Okay, so X-rays are coming and then they produce electron-hole pairs within the semiconductor material. Then by applying voltage to the ends of the diode, the hole and electron pairs are separated and they rapidly move in opposite directions, and you can produce current, and you can measure the current by using the wires here at the end of the detector. Okay, so what we have done, again, we have converted X-rays to the currents, okay, by using electron-hole pairs. In case of gas ionization chambers, we are using electron-ion pairs. In case of scintillation counters, we convert X-rays to the electrons. Then we produce current. So in gas ionization chambers, in proportional counters, in Geiger counters, in scintillation counters, in semiconducting counters, we are doing the same. We convert X-rays to the currents, okay? Then we measure the number of the X-rays, we measure the energy of the X-rays. This is the main mechanism in many types of X-ray detectors. Do you have any question here?
No.
Here there is a very nice paper article published in MRS Bulletin in 2017. So you can find much more detail concerning semiconducting materials used for X-ray detectors. And you can find also comparison between silicon, germanium, gallium arsenide, cadmium telluride, and also CZTs for applications in semiconductor detectors. Oh, I will finish with the CCD detectors. CCD means charge coupled device. This type of X-ray detectors have replaced photographic film as the detector of choice for medical imaging, and they have many advantages compared to the photographic films. You can store them, you can manipulate them, okay? Or you can send them to the other places, other computers, other doctors, let's say. So they have many advantages, and mainly they have two types, direct and indirect CCD X-ray detectors. In the direct method, X-ray photons are absorbed by directly CCD, but in case of indirect method, I will go into detail, I will show you pictures. X-ray photons are converted to visible photons, first of all, and then they are absorbed by CCD, like in scintillation counters. In scintillation counter, first of all, the incident X-rays are absorbed by scintillator crystal here, and then they are converted to the light photon. And also in indirect method, in CCDs, X-rays, first of all, converted to the visible photons and then absorbed by the CCDs. So why the name is CCD? What is the meaning of charge coupled device? Here you see a schematic picture of a CCD sensor, let's say. So what we have here, we have many picture elements, okay? Generally 1,000 rows here, 1,000 columns here, okay? We have many picture elements, and these picture elements are called shortly as pixels, okay? We have many pixels, and each pixel measure the incoming X-ray intensity, okay? So how to do that? When the light comes on this pixel, okay, an electric charge is produced, because these CCD detectors are also made from semiconductor materials, mainly silicon, okay? So when X-ray comes on this pixel, then you produce charges, okay? You produce electrons, and then you convert these electrons to the currents. Then mainly you convert incoming X-rays to the currents, okay? So let's consider that here on this pixel, let's say 3 X-rays are coming, okay? And here in this pixel, only 1 X-ray is coming, okay? And here we have nothing. So depending on the number of incoming X-rays, you produce here more charges, and you can measure more current from that pixel, less current from this pixel, because just a single X-ray comes on the surface of this pixel and you have nothing here. So then by using the computer programs, you can convert these charges to the two-dimensional pictures, okay? The more or less the same mechanism is used in the CMOS sensors, complementary metal oxide semiconductors, but they have some differences between CCD and CMOS sensors. I will also talk about this one. So what about the indirect method in CCD detectors? Let me also tell you something more on this issue. So here in the indirect method, we have an X-ray photon, and here we have a screen, a phosphor, okay? So this is placed in front of the CCD detector. This is the CCD detector, and this is the phosphor screen, and incoming X-rays interact with this phosphor material, and then due to the absorption mechanisms, incoming X-rays are converted to the visible light photons, and by using optical methods, you direct these visible light photons to the pixels of the CCD sensor here, okay? This is the indirect method. So you lower the energies of incoming X-rays by using indirect method. So these are the CCD detectors. And now I would like to compare the CCD detectors with the CMOS sensors. Here you see a CCD array. We have many pixels in this picture. And here a CMOS sensor. There are also many pixels here. So photons are coming on these pixels. Photons are coming on these pixels. And you produce electrons here. You produce also electrons here. So then these electrons converted to a voltage, okay, here at the end. Also in the CMOS, this charge is converted to voltage, okay? But what is the difference between CCD and CMOS? The charge to voltage conversion is done here at an output node in CCDs. But in case of CMOS, each pixel can do that, okay? Charge to voltage conversion is done here within each pixels in CMOS sensors. For this reason, the production procedures for the CMOS sensors are more complicated compared to the CCDs, and then of course you can understand that they are more expensive, okay? So mainly in many applications, in medicine, in astronomy, for scientific purposes, so CCDs are used, but recently due to the developments in lithography processes, CMOS are also developing very fast. So this was the difference between CCD and CMOS. Do you have any question related to the CCD detectors?
No, it's clear.
Okay. With this transparency, I have finished the X-ray detectors. As I told you at the beginning of my talk, there are also many other different methods, okay? So in addition to the methods which I have mentioned here, in some new types of X-ray detectors, combination of these present methods is also used. So for example, scintillation method and CCD method are used together in newly developed sensors, and also thin film transistors, TFTs, are also combined with the CCD detectors, CMOS detectors. So there are many new methods. For example, there are semiconductor drift detectors, but I will not go into detail because I'm not expert on each type of these detectors. I'm just a user of X-rays. But if you know the basic information of the X-ray detectors, which you have learned during this lecture, you can easily understand the working principles of the other X-ray detectors. What you have learned here, you convert X-rays, you convert photons to the electrons, to the charge, to the current, to the voltage, okay? So this is the main mechanism which we use in X-ray detectors. In addition to that, if you know the absorption processes between the X-ray and matter, you can easily understand the mechanism of the X-ray detectors. Do you have any question?
No, thanks.
Okay, then take care of yourself. Bye-bye.